Yeah. Okay, students. So let me put my second flip. So what this should do is this should make it very clear for you about the phase diagram. We already talked about why phase diagrams are constructed and what goes into constructing the phase diagram, and these are equilibrium diagrams. So all that we discussed, but now when we look at specific this phase diagram of temperature and volume and pressure and volume, so what are the different regions and what are these lines, what are these boundaries, and if you are at certain locations, what state is the material in, and if you are at an initial state and then if you change or move to another state, how do you represent that in the diagrams? How do you draw the lines? Why am I saying all this is everything can be depicted on the phase diagram about what is happening with the material. So even if you have a numerical problem and if you are clearly able to show the TV and the PV phase diagrams and show initial state and the final state and how it is changing, if you can show that, that means you have completely understood the question. Afterward, it's just a very trivial thing of opening the appendix, looking at the tables, looking at the values, and just writing it down. That actually, I would say, is very trivial and unimportant. So even though it is a numerical problem, you still have to understand the concept. You have to visualize what is happening to the material and how it is evolving, and then you should be able to depict that in the diagram. If you can do that, so actually we should set the questions in such a way that right at the beginning we should ask you to draw the diagrams, because if you draw the diagrams and if it's correct, that's it. There's nothing more. Afterwards, your numbers actually don't matter because anybody can look in the tables and can write down the numbers. So let me start. So why are we even having a TVPV diagram? Because when you looked at the vapor pressure curve, the PT diagrams of a transition of liquid water to saturated, or not, of a liquid water transitioning to vapor, you know that the energy is going to be absorbed as the liquid is going to transition and the pressure is going to remain constant. So the temperature remains constant because it's endothermic. Temperature remains constant, pressure remains constant, liquid starts to vaporize in small amounts. It's not like zippity zappity. It does not happen at an instant. It happens slowly. And then what is the property? What is the variable that's changing? It's the volume that is changing. But we drew a PT diagram. So there's no volume. We cannot see the volume change. So it just looked like as though it was a point. So if I just change the temperature a little bit, I went from the liquid side and I fell into the vapor side. But it doesn't happen instantly like that. It happens with the volume change. So that is why we need to draw TV and PV diagrams. That's one thing. The second thing, in the TV and the PV diagrams, like I mentioned in the class, you can also select a pair of T and P, so that as in real world industry application, you can decide which pair of temperature and pressure that you want to use for you to boil the liquid and transition it to vapor. Like if you're a boiler guy, you can make a call for different materials, or if you're using a refrigerant in a compressor, in a refrigerator, in a air conditioning equipment, so you can make a call with the phase diagrams as to what pair of temperature and pressure that you can use for phase transition from liquid to vapor and vice versa. So it's not just heating, it's also cooling. So you can decide what you want to do, so it's like you can work on the economics by knowing what temperature and pressure you want to use, because both temperature and pressure, which is unrealistic, will cost you money, because these equipments are really big and they're not going to be working for like a few minutes or such. You may have to use it for hours and hours. So the cost will come into play. That's the second thing. And the third thing is, just remember, I already said this, so at each point it is a pair of temperature and pressure, so both are changing. So without much ado, let's get into drawing the diagram. So hope the pen's working. Okay. So I'm going to draw the TV diagram. So everybody draw the diagrams really well, label them. Okay, it's very intuitive. I'm at a very low volume here and at a low temperature. So what state the material would be? It would be a liquid. So what do we call this liquid as? Compressed liquid or subcooled liquid. Now go to the other region here, high temperatures, and the volume is also pretty high. So intuitively, what state the material will be in? Superheated vapor. Superheated. So then it's very intuitively, it's obvious for you to know what this region between liquid and vapor would be. It has to be a mixture of liquid and vapor because the transition does not happen instantly. You are going to have some amount of liquid transitioning to vapor before the entire amount of liquid goes to vapor. So if that is the case, and how does that go? So it will start at this point because you are heating. So it will be isothermal temperature. So it will go from this line. So what do we call this line as? It is the, so I will mark this as A, C, B. So the line AC would be the interface between liquid and the liquid and vapor where they coexist in equilibrium. So this would be the 100% liquid. So what is it? It is completely saturated liquid line. So then you go to this side and look at line BC. As you're heating, the liquid becomes, a little bit of it becomes vapor, then some of it becomes vapor, 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 and then finally what happens? The entire beaker or the container will be having 100% vapor. So it is saturated vapor. Now the material has become completely saturated in the vapor state. So what is this line? Saturated vapor. So are we clear? The line AC is a saturated liquid line and the line BC is a saturated vapor line. So you're going to transition from a saturated liquid state all the way to a saturated vapor state, from 100% liquid to 100% vapor. And when you go beyond that, you're not saturated, because we say saturated because we are talking about steam. So steam will have various qualities. Qualities means how much vapor does it contain, how much water does it contain. So if it's completely saturated with liquid, then it's a saturated liquid steam. But then it keeps, you keep heating, then the quality improves, you get more vapor, then you get completely saturated vapor steam. But you don't let up, you keep heating furthermore here in this region, you get superheated vapor. So it's not close to being a two-phase anymore. So what do we call this region as? Single phase. This region as single phase. This region, yeah, I can call it as, yeah, it's a single phase region because you have only liquid phase. Here it's a single phase region, you have only a vapor phase. This is a two-phase. So from now on, when I say you are at the two-phase region, you are in the two-phase region, I think you should know by now where you are. If I say you are in the single-phase region, then you should know where you are. You could either be a liquid, compressed liquid, or you could be a superheated vapor. So now we'll take an example here. So let me erase a few things, like all this labeling not required. So I think by now you should understand that any more labeling is not required. Got it? I think you can purely write TV diagrams and you can do away with, right students, you can do away with labeling. So remember, each point of this on the saturated line and the corresponding point on the saturated vapor line, saturated liquid line, and so they correspond to both temperature and pressure. So we will call this point where you have a pair of saturation temperature and saturation pressure. So remember, it's not just T that is changing in constructing this phase diagram. We are changing both temperature and pressure. But can I show pressure change here? No. How do I show pressure change? I have to draw a PV diagram. I will get to that part. So now let's be on the TV diagram. So you should draw both TV and PV diagrams for the numerical so that you're very clear. And once you are clear with in depicting what is happening with the state, initial state and final state on both the diagrams, then you are good to go. That means that you are perfect. You really understand the problem. Okay, so now since you are not in class here, it's a flip. I am somewhere here. So what am I? I'm here. What am I? I am a compressed liquid. So now I will, let's say I am a compressed liquid at some pressure. Let's say some pressure, X megapascal. So I start heating at this constant pressure. So what will happen? I start heating. So I'm ramping. And what happens? What do I touch? I touch the saturated liquid line. When will I actually touch the saturated liquid line? Because I started with a certain pressure, a constant pressure. When will I touch that saturated liquid line? I will touch that saturated liquid line when my temperature attains the saturation temperature corresponding to that saturation pressure that I have started with. So only then I reach the saturated liquid line. Now what happens? I don't let up. At that same pressure, constant pressure, I still keep heating. So what will happen? The liquid will start to endothermic. It's endothermic. It will start to take in the heat and it will start to phase transition. So it's little bit vapor, 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 and it becomes completely saturated with vapor. So I reach the saturated vapor line and the pressure is still constant. Now I still don't let up. I still keep heating. What will happen? I'm ramping. Now this saturated vapor will again start to heat up and the volume also will change. So what did I get? I started with 1 at a constant pressure. I started ramping, but I do not know when I will reach the saturated liquid line, but I do know I will reach the saturated liquid line when I attain the temperature corresponding to that saturation pressure. So I attain, I come here. Then what happens to the material? It starts to absorb heat and the liquid will start to transition into vapor and you will reach point 3. You still don't let up and you still keep heating. Now what happens? There is no more endothermic event there and the gas starts to, saturated vapor starts to expand and it becomes a superheated vapor. So this is the first thing that you should be very clear with as to what happens if you're ramping at a constant pressure. So what were the different regions that you entered? You were a liquid, then you became two-phase, and then you became a vapor. So single phase, two-phase, and back again to single phase. So if I know what pressure this is, now let's say this pressure is, let's say 1 megapascal. I say that I started heating a liquid under pressure of 1 megapascal. No problem. You can easily tell what the temperature will be at 2. Because you can go to the table and you can see for 1 megapascal saturation pressure, what is the corresponding saturation temperature. So bang, what do you do in the diagram? You can easily draw 1 and 2 and you can tell what is the temperature here, and obviously you know that you are at 1 megapascal, you are done. You can label it right there. And then you heat, nothing will change, temperature won't change and the pressure won't change. And then in the problem maybe we will say that you continue to heat to another temperature of something, T2. So then you know T2 there. and the pressure does not change. That's it. You draw the diagram. It's that simple. Just don't forget the diagram is in such a way that each point corresponds to a pair of saturation temperature and saturation pressure. I'm harping on that over and over and over. So don't keep looking at temperature and pressure as individual entities. They go hand in hand. And what do we have here at the critical point? You cannot differentiate between the saturated liquid nor the saturated vapor. So that is where you reach the critical point. You cannot differentiate the two phases. So above that, what do you have? Nothing. You have a single phase. Well, let's just say it's a fluid. That's it. It's a single phase there above the critical point. So what is above critical point means? Above the critical temperature and critical pressure, you cannot differentiate between the two phases. You have a single phase. So we'll call that as a fluid. So this is how it goes. It's as simple. Now, if I ask you, if I tell you that I started one, and I'm at 1 megapascal, so obviously I say I keep heating, so you will reach point 2. You know what point 2 is from the table, and then I will say you keep heating until you have 30% vapor. So I will say until you have 30% vapor. And what is the volume? I will ask you what is the volume when you have 30% vapor. So obviously you know this line, you can break it up into 30%. You are here because you have less vapor, so you are still close to the liquid line. So you are somewhere here, 30%, and you just come down here and you can calculate the volume. But you don't have to do this by eyeballing. You can easily, this is called a lever rule. You can determine, so if I have like 2, 3, and if I put x here, I can say what is 2x? What is the percentage at x? X actually have to write Vx minus V2. This distance divided by the entire distance will tell you what fraction of vapor is there. It's called the lever rule. So this distance divided by the entire distance will tell you how much liquid is there. So how do we look at it? To go to a new one.
Right.
So again, let me draw this and make it clear for you. T, V. Okay, we are traveling from here to here. So Hyderabad to Bangalore, and I'm somewhere here. X. What is the total distance from Hyderabad to Bangalore? B minus H. That is the total distance in terms of volume. I am at X. So I'm at X. So just by looking at the plot, am I close to Hyderabad or am I close to Bangalore? So obviously I'm close to Hyderabad. So does that make me more of a Hyderabadi or more of a Bangalorean? Obviously it makes you more of a Hyderabadi. So that means it is how close I am traveled from Bangalore to Hyderabad to be a Hyderabadi. So which distance is that? This distance. Now do the other thing. How much of a Bangalorean I am? That is dependent on how much distance I have traveled away from Hyderabad towards Bangalore, which is which distance? This distance. Okay, now it's clear. How much of a Hyderabadi is how much of distance you have traveled from Bangalore, away from Bangalore towards Hyderabad. How much of a Bangalorean are you? It is the amount of distance that you have traveled away from Hyderabad towards Bangalore. I think now you should not be confused. So how much of a liquid I am? I'm liquid here, I'm vapor here. B minus X divided by B minus H. How much of a vapor I am? How far I have traveled from the liquid away towards vapor, which is what? X minus H divided by B minus H. So how do you get this lever rule? You can easily derive it. You can take conservation of volume, so you can derive it. You take total volume is equal to volume of liquid plus volume of vapor, the entire volume. So convert that to specific volume. How do you convert that to specific volume? So you have V equals V liquid plus V vapor. So you can, anybody can do this. So you can convert this to specific volume, divide by mass. So you got specific volume. So here you got what? Divide by V liquid divided by, yeah, you got V liquid divided by mass plus V vapor divided by mass. So how do you convert this volume liquid into specific volume? So how do you convert this to specific volume? So specific volume is M liquid multiplied by, did I do it correctly? M liquid multiplied by specific volume of V liquid divided by M plus M vapor multiplied by specific volume of V vapor divided by M over. M liquid by M is what? Mass fraction. So you can just call this as mass fraction X. And M vapor by M is 1 minus X. So I should put specific volume V liquid 1 minus X V vapor, and this is equal to total specific volume. So I should put TOT here. TOT, this is full volume, this is specific volume. I have written lowercase. This is still full volume, this is still full volume, and this gets converted into mass and specific volume. This gets converted into mass and specific volume. Divide by M and X. So what is X? Or I should write it the other way. We usually write X is equal to M vape by M. So let me just do that correctly here. So erase this, erase this, erase this. So M vapor by M is X. So what should be here? 1 minus X. So what should I write? V liquid. So in the tables, guys, you will not have specific volume as V liquid as V liquid. You will have it as V subscript F. This guy, you will have it as V subscript G. And then total specific volume will be V. That's it. This is your liver rule. So if you have any questions, tomorrow you can ask me again. So that's the first thing. So you should learn how to draw the diagram, and you should know at what state you are in. So since we are on this, let me now quickly draw pressure versus volume diagram. So because you have to represent the same phase transition that you did with temperature, it can happen with changes in pressure also at isotemperature, correct? So now let's say you are at some temperature like, I don't know, some temperature like 85 degrees, 85 degrees, and you are, what will you do for you to reach the saturated liquid line? You are at 85 degrees. Will you increase the pressure? So you are a compressed liquid here. For you to reach for 85, so you are at an isothermal temperature, 85 degrees. So how do you know when you will reach the saturated liquid line? Just like the TV. Will you increase the pressure and will you start to become a vapor, or will you decrease the pressure from a liquid state? Think about it. Will you go up or will you go down for you to reach the saturated liquid line? So what will that pressure be? It will correspond to the saturation temperature. That saturation pressure will correspond to the saturation temperature of 85 degrees. How do I know what pressure that is? I go to the table and I open B 1.1 or 1.2. For 85 degrees C saturation temperature, I see what is the saturation pressure. That is okay. You will get that and you will know that that is a point where you will be a saturated liquid line. That is fine. That is fine. But my question is still, you are at somewhere here. So for you to reach the saturated liquid line, Will you increase the pressure or will you decrease the pressure? Because your goal here is to do what? By changing pressure, you want to convert the liquid to vapor. So obviously, intuitively, you know that you're going to decrease the pressure and you're going to come somewhere here, and when you come here, that 85 degrees will correspond to the saturation pressure. So you don't let up, you still keep changing the pressure. What happens? The liquid will start to transition and become vapor. You still don't let up. What happens? Now the saturated vapor will start to increase in volume further and it will start to go into superheated vapor state. So you started with 1, you reached the saturated line 2, then you became saturated vapor 3, you didn't let up, you still kept changing the pressure and the volume kept increasing, and then you became superheated vapor of a very high volume. So become very comfortable with this. The temperature you are going up, the pressure you are coming down for you to convert the liquid to vapor. So I think you can stop here.